Prof Rudolph this morning for a web chat. He is a professor at the Technical University of Agricola in Germany. And he's going to talk about geospatial monitoring for a changing landscape. So with that post-mining perspective, and I think there's a lot of learnings that we can take from them because the mining in Germany is so mature. So they've already moved beyond mining and into that post-monitoring phase where you can use monitoring technologies to observe how the landscape is responding to that, and then also to prioritize your interventions based on that. So we're looking forward to listening to you, Professor. Thank you very much. Just to mention, so you will be able to ask questions. He's going to present a few slides, and at the end of every section, you'd be welcome to ask some questions. So just raise your hand, and then we'll deal with that section by section, and then also at the end. So thank you very much. Over to you.
Yeah, Helen, thanks a lot, ladies and gentlemen, and good morning, everybody. My name is Prof Rudolph. I'm a professor at Geospatial Monitoring in Germany, and I'm very happy to be in your group this morning, and I like to share my experience I have in post-mining, in geospatial monitoring in post-mining. I will share also afterwards the slides, so if you have questions, bear with me. There are several sections, chapters, where you can raise your hand. A quick word on my person. I'm a geologist by background, and let's say working as a subsurface expert now on geospatial monitoring is a little bit odd, but I feel myself a little bit as a kind of frontier runner between the disciplines, and this is very, very important, I have to say, for the analysis of geospatial data, specifically in post-mining. Before I start, I would like to give you a little bit of an overview on the topic. What is post-mining? I'm working in a research center of post-mining, and we are looking at all the different aspects of post-mining here in Germany, but also internationally. And we see that post-mining is the phase which comes after the operational phase, when the operation ceased and the raw material production stopped. We see also post-mining as a wide field for exciting research and application, and it's important to mention that post-mining encompasses a lot of different disciplines, otherwise you fail in your analysis. We do this already for a couple of years. I'm based in Bochum, Germany, the heart of the former German hard coal district, and I'm located at the Technical University Georg Agricola. Our name's patron, Georg Agricola, is the founder of modern mining. 500 years ago, he wrote a very famous book on Dere Metallica. It's the first book on mining. Since 1816, you can study, things related to georesources. In the past, it was really the engineers for the mining, and nowadays it's more than that. You can still do some things on georesources, but you can do also mechanical and electrical engineering. So it's a technical university. Within the university, we have a research center of post-mining, and we see the challenges of post-mining from 4 different views. In the first place, it's the focus on the perpetual tasks and the mine water management. Second, on post-mining, geospatial monitoring. The third one is a little bit an unusual one, but we see, at least in Germany, at one stage that people trying to, or at least people are identifying themselves with the former mining and the mining objects, and it's now a question of keeping these mining objects like former shaft towers or other installations, and it's a matter of material science to keep that. And besides the 3 engineering aspects, you also have a fourth one, which is on the reactivation and transition, so in principle land use and what comes next after you finished your technical work. Our team is quite interdisciplinary, and that is already something which I like to give you as a take-home message. When you look into post-mining, you need a very heterogeneous team with different disciplines. These disciplines should be integrated, and that gives you a nice overview on the analysis of post-mining challenges. Our institute is quite big, so in principle 40 staff are working on these aspects, and that demonstrates maybe also to you that post-mining is not, let me say, back office discipline. It's really something which is in the mind of the people here in Germany. We are even at that point that you can study post-mining. We are currently in the phase of changing the market. Pardon? Okay, so we are in the phase of changing that master program, and by winter term 26, we'll have georesource engineering with the subjects on mineral engineering. So, better now? My mic was muted for some reason. So you can do the master program and enjoy, let me say, very technical things on post-mining. We try to involve the students in different types of mining and get them a full master program. If you're interested in that, check later the link here, but be aware that we are currently in the change from a very German language-based master program to an English-based master program. That master program, as we see also in the post-mining challenges itself, is quite international already. We have about 20% international students from different countries currently, or from Africa. In the past, we also had students coming from South America and other countries. When you ask yourself now, why post-mining in Germany? That is for us a very big challenge. In principle, Germany, if you might have not known it, is a mining country, and it's not only about hardcore mining or lignite mining. It's in principle the entire suite of raw materials we produce ourselves in Germany. So, because the entire country is affected, you need to ask yourself also what comes after you finish mining that raw material. And that, let me say, peaked in the question when we closed the hardcore districts. You see them here on the map. You see here the hardcore districts, so quite dominating in Germany. But what does that mean compared to South Africa? And I want to share you a little bit the size, the extension of our post-mining regions with your country. So what I show you now is same scale. You see here in Johannesburg, Pretoria in the middle. And I put now in the rural area, maybe the size of the wider area of Johannesburg. We have the three big lignite mines. Again, something similar to the size of Johannesburg. But we also have Lower Saxony, a country which is really dominated by oil and gas production. Thousands of wells drilled in that country. So more or less the entire country is affected by mining. So our problem is huge, but compared maybe to South Africa, is not as same size as say you have. But still, the challenges are high, and here are some 3 examples that you understand why we are looking at it from a research perspective. As I said, Lower Saxony, a lot of deep wells drilled. North Rhine-Westphalia, where I'm based with Bochum, we have the former hard coal mines, and we still have to deal with about 60,000 shafts. That's a huge number. In principle, yeah, more than half of the state is affected by mining. Saxony in the east is a little bit different types of mine, a lot of ore mines from the past, but still 70% of the area of Saxony is affected by mining. So that is a huge problem for us, and it requires a lot of work to solve these issues and to get back to a state where the nature is in a stable environment. Some more deeper insights in the rural area. Again, rural area the size maybe of wider Johannesburg and Pretoria. We face here 500 years of mining, 100 years of industrial mining, and you see here a map of the, that's wrong here, of the shafts. Different distributions in the south, a little bit more than in the north. So post-mining challenges here in the south are quite high. And you see that on the next map with the sinkholes. There are still sinkholes happening every year. And this is in a residential area with 5 million people living. And a sinkhole development can really, let me say, disturb, for example, the motorways, the railroads. So it's a big deal for us here in the rural area. On top of that, we are facing huge subsidence due to the underground mines. And just check out here the color scheme. The darker the color, the deeper the subsidence. And we face in some areas here subsidence of about 25 or 25 meters. This is huge. Yeah. And again, think about that this area is a highly populated area with 5 million people, and the subsidence of the past is still causing problems. Our main problems in the rural area, and this might be a little bit different to South Africa, but water is also for you an issue. But here's some numbers of our challenges. In the rural area, we pump about 1 billion cubic meters of water, of surface waters, with 600 pumping stations. This is a huge effort, because if we wouldn't do that, we would create lakes at surface. So we have really a serious issue here of getting the water pumped in these polar areas, also these subsidal areas. Otherwise, we create huge lakes. In some areas, it looks like this. The nature is affected. It was allowed to, in some areas, to create these lakes. This is really disturbing the nature. You see these dead trees here in the background. But nowadays, because mining ceased in 2018, nature is kicking back and is taking over these disturbed areas. And we are trying to get these kind of anthropogenic affected polar areas now back into new natural habitats. So from a challenge to opportunity, and people are accepting that. And this is really something for recreation, sport, and so on. Just to complete the story, here you see the dots of these pumping stations. So more or less the entire region is affected by these subsidence areas and the polar areas, and water needs to be pumped everywhere. If you would stop these pumps, the rural area, the rural valley, would be at least partially flooded with water at surface. Besides these surface waters, we need to pump even more waters, and this is 100 million cubic meters of mine water. This is the water coming from the mine, so the deep water. And the water is pumped currently with 6 big stations. You see here a map. The dark blue are these future or currently used pumping station. In principle, because the subsurface is so disturbed, the mine operator designed the subsurface in that way that the water from the mines here in the heart is flowing more or less undisturbed to the west, and gets then pumped here in the west, and then the water is pumped into the River Rhine. We have some exceptions here in the south due to the long-lasting mine operations here, and a special case to the east. But in general, the water is flowing through the former mines from the east to the west and gets then pumped at the west. We still have some backup stations if that model is not working, but so far the water gets pumped, especially here in the west. The station looks like this, and again you see how post mining works. Yeah, you have here the former mine, the shaft tower, which was a ventilation tower in the past, and that in that shaft tower the water is pumped, and the water is then pumped to the next river Ruhr in this case. But because mining stopped, and you see that people start moving in these former mine sites and taking over these former mine sites. That is in principle a huge task, and this kind of perpetual eternal work is done by the RAG Foundation, a foundation set up by the former mining operator, the RAG AG, and the foundation has three tasks to do. It's taking care of the mine water rebound, so the rise of the mine water within the mine, so taking care of these 100 million cubic meters of water, taking care of the polar management, so the pumping of the surface waters in the subsidal area, so these 1 billion cubic meters of water. And there are still some cases, former sites, which need to be cleaned, especially the groundwater needs to be cleaned. But these are the three tasks the RAG Foundation needs to do. And just for that job, we are spending about 300 million euros per year. So this is a huge, huge task. And you see, improving the understanding in one of these SARs and lowering the money spent, this is why researchers like we are looking into these questions. So that's for the start, the introduction of post-mining that you see. We have quite some experience here in Germany, and we are looking at the closure of mines, not just from an operational perspective, but also from a research perspective, because the problem is so huge and it's affecting so many people that you need to have some researchers, some scientists who are developing new concepts to get back to an unaffected nature and trying to get from this challenge to an opportunity. I would quickly ask you whether you have some questions. Otherwise, I would keep going with the next chapter. Please raise your hand or drop your questions.
Okay. I don't see any questions. I think we can carry on for now.
Right. Good. So coming to the topic of today's morning, geospatial monitoring in post-mining areas. If you look into, let me say, the life cycle of georesources, you're probably with me. In the past, it was kind of you found something and you collected and used it. Nowadays, it's a little bit more complicated. The, let me say, operational cycle is a little bit more splits, and you go through different stages. But my, let me say, player is already here. Even if you start, well, let me say, when you start with exploration, you start with your first ideas, consider already this kind of geo-environmental monitoring and keep that monitoring through the entire operational phase, and even integrate here external factors like the climate change, the change in precipitation, or the drought periods, because the water is the thing which is affecting more or less the entire mine life cycle. And what my player is here also is, let me say, when you do that properly, you understand your cycle properly, you are able to get to a process understanding of how the processes in your area are developing. And if you compare that with other experience around yourself, your operation, you are then able not only to do geospatial monitoring, but you get to this kind of geospatial digital twin. In an environment, in an operational mode, we know already this concept of a digital twin, that you kind of design your entire production. And I think it's worth thinking that digital twin even bigger and integrate the effects of geospatial monitoring within your cycle, within your operation, to ensure that the footprint you are creating with your mine operation is as small as possible, that you understand your influence of the nature, and this is also, we say, the value of a proper geospatial monitoring. You can also involve the public in your operation, because with monitoring, and you see that later a little bit in the exercise, you can create a lot of transparency. When we now look into geospatial monitoring, I created here a little bit of a house where I put the bricks in with different tools. That is not limited to that tools, but it should demonstrate already that geospatial monitoring is a huge task, because you need to be able to work with different tools, get the results properly analyzed, get them set in a perfect perspective to other tools, and create your understanding. And surely you need to involve in your, let me say, analysis, expert knowledge from different disciplines. Otherwise, you fail. I'm creating always that, I'm using always that kind of image that geospatial monitoring is really like playing with a big jigsaw, where you need to explain the motif of the jigsaw, but you don't have all the proper parts of the jigsaw. So geospatial monitoring has some requirements. So you need to be able to do spatial temporal thinking. Yeah. So you need to be able to think backwards and forward. Yeah. You need to understand the history, but you need to understand also what's coming next. So in principle, geospatial monitoring is an n-dimensional problem, if you like. So you have to consider X, Y, Z, or depths. You need to consider the component time, and then your sensors, your different sensors. And all your sensors give you different answers, and you need to incorporate that in your analysis. I'm sure that some of you like that, and some of you don't like that. I see that also with my students. That's not something you need to worry about. But if you think this spatial temporal thinking is not my job, is not my arena, then pull in experts who are willing and able of doing that. Yeah, this is quite a complex way of thinking, quite a complex way of analysis, and you need to have the proper experts who are capable of doing that. So I show you now a couple of applications. A little bit go through my projects. Bear with me that these are projects more or less related to Germany, not so much to South Africa. The exercise later is related to South Africa, but I want to show you with these projects in Germany how that works. And I'm starting already with quite a complex project, just to show you that geospatial monitoring is extremely helpful, but on the other side, you need to be able to work through a lot of data sets. A drone photo of a mine site. And if you don't watch carefully here, you wouldn't spot these well pads here. And this is a drone photo of the biggest underground gas storage we have in Europe. In that side, or on that side, we talk about 114 caverns drilled and solution mined in a depth of 1,000 meters, out of which 100 caverns are used to store throughout the year different types of gases, natural gas, helium, and also hydrogen is coming up. That mining operation affected the surface. We had in the past a serious accident in the place, so the public concern went up. Public reporting wasn't good, so a lot of discussion around. And if you look carefully in that area, we have bog areas, we have local rivers. So the analysis of the ground motion, which is of biggest concern in this case, is already a little bit complicated because you have overlying influencing factors. And due to the public reporting, it was required for us to set up new ways of collaboration and public participation so that the interested public is involved in the monitoring of that site. I put down the link. You can check out later what we are doing here. For 4 years now, we are applying remote sensing technologies, radar remote sensing technologies to monitor the ground motion, and also setting up processes where we involve the public. But back now to the technical challenge. We have a lot of data to analyze if we want to understand in a mine operation in the ground motion. Subsurface mining, as said, at 1,000 meters depth in a thick salt layer, but still it's creating subsidence at surface. And in that area where we have an overlay with former bogs and with rivers, little waterways, water bodies, there's a lot of ground motion happening anyway. And even we in Germany, we are facing the climate change. We are seeing a drop in groundwater level. We're seeing changes in soil humidity, and this is creating a lot of ground motion here as well. And the bog area was in the past much bigger than nowadays. So we have a lot of organic soils around, which are also affecting the ground motion. So if we want to apply radar satellite remote sensing to detect the ground motion, we need to have a lot of information, geodata in the background to understand the influencing factors of ground motion. And if you are with me now here, getting a proper analysis of these different data sets is already a big task. Bringing that into public participation in collaboration, it's a huge task. And this is where we were pulled in as scientists to run that process. A couple of figures here, how that works. I can share with you even more photos of different events. We are at different official meetings, like municipality meetings, with different members of the city, at general information events where we explained the information here. For example, you see how our cavern is looking like. We designed a bicycle tour with interesting people. There were kind of 40 people driving with us through that area, and we were explaining how underground storage works and how that is influencing the surface. Surely went also into the bog, and I pulled my students also into that area to get a proper understanding. So very nice project, but a challenging one. But at the end, we were able to create a map of ground motion, and we are updating that map regularly on a yearly basis. And if you look into that map carefully, you see here the isolines of ground motion based on the mine surveyor's map. The orange, reddish, yellowish colors are the analysis of ground motion based on radar satellites, and the map looks different to the map of the mine surveyor. The ground motion is much more heterogeneous. You see here a kind of patchy reddish ground motion, which is a little bit higher. And here in the outskirts, you see that the ground motion is reduced. But again, there are also areas where you have an increased ground motion. And if you look carefully, for example, at that area, you see that a little river is running through the area, and these kind of floodplains around the river are areas where you have also increased ground motion. So we were able, with these maps, and we are still doing that, and pushing this also into these information events to take the public with us, we were able to describe with these maps in principle complex ground motion, surely influenced by mining. Here in the center, then to the western part, the bog areas in general, a lot of fluctuations in the groundwater, changes in soil movement, soil humidity due to climate change or precipitation events happening or not happening. And surely, based on our analysis of the buildings, we could also demonstrate that cracks in buildings are not primarily related to mining or the other natural influences around, but are more related to the bad construction of these buildings. So with this example, you see that geospatial monitoring gets quite complicated if you want to do proper understanding in a mining area. Even though the map looks a little bit patchy, to transfer this to South Africa, in non-vegetated areas, these analysis is even better, because with radar satellites, you look at the surface, and the radar satellite can't distinguish whether there's a tree or it's open land or it's a residential area. To get the influence, for example, by moving trees out, you need to look at bare soils, bare surfaces, and so non-vegetated areas are even better for the analysis than the ones we have here in this cavern storage. What else can be done? Some more examples, the application of the tools. I'm starting here. Sorry for that slide being partially in Germany. We did optical imaging here with a drone. We monitor a particular site where the rehabilitation process finished and vegetation was put in place. And we were interested in seeing how the vegetation kicks in once the, mining influence ceased. And we put also into that area down a ground sensor to measure the soil humidity. And you see a change in soil humidity here, also on these photos. This was important for us to understand the kind of success of that renaturation measures. But we could also demonstrate at one stage that we had a heavy rain event here. And you see that here on that photo, the heavy rain event was so devastating that it's kind of dragged down all the sediment of this little creek here, this little water body, into this little lake, and in principle destroyed the little early vegetation in these areas. So optical imaging, for a start, is a good point, and if you do that regularly here, like on a monthly basis, you can see how your rehabilitation processes work and whether you are successful with the growing of vegetation and the interaction in this case with water of a little water body, little creek. Other application is if you use not only the visible light, but you use also the non-visible light, in this case multispectral analysis, so using the near infrared outside our wet view of our eyes. Plants are extremely reactive to that light, and if you do analysis on this infrared changes, it's called multispectral, then you can see how the health of the vegetation is. Here in this comparison of the optical and the multispectral image, it's maybe not so drastic, but you see the kind of influence areas quite sharply visualized here. If you look into that image here at the bottom, a little bit of different way of plotting it. You see where these pipelines are buried, even though the canal is kind of filled up again with sediment, and it's again in agricultural use, but the change due to the kind of buried pipeline is still existing, so the vegetation is reacting, and you see the poorer growth in the change of red color. The redder the color, the more healthy vegetation is. And here, obviously, the vegetation is reacting to the former construction site. If you take that even further into thermal imaging, we did a pipeline check here. And if I zoom in into that photo, you see that in some cases here, you see still how the construction is influencing even the thermal response of the surface. So what I'm saying is here, using thermal as well as multispectral imaging is again another enabler for your geospatial understanding, how mining is influencing the surface. Sorry for that. If you push that further, and you saw that with the regular drone flights, and the same with satellite imagery, the amount of data you are creating is huge. And therefore, besides the expert knowledge, you need to analyze the data. You need to introduce into your analysis also automatic object classification to understand, get a pre-processed data set that helps you understand what you see at the surface. Here in this case, it's a gas storage surface facility. We are looking at it to understand where potential methane leaks can occur, and helped us to classify the several 100 meters by 100 meters large facility to understand even properly. The next stage is then on geospatial monitoring is looking into gas components in the surface around these operations. Here in this case, an example for gas sensor based on a drone. That is the kind of bad looking sensor here on top. We have here a sensor which is able to measure CH4, methane, CO, CO2, H2S, other hydrocarbons, and helps us to do some leak detection. But CH4 and CO and CO2 are also gases which occur naturally in our environment. And if you look at these maps here, you see some increased values here. These are values not related to some technical installation, so a leaking pipeline, for example, but they are related to some changes in the natural environment, that you have maybe here some rotten trees, plants, whatever, and these are creating CH4 emissions, which you can measure. So again, when you do that analysis, you need to understand the area where you're looking at. Either you need to understand where you have some operational influence, or you need to understand, for example, soil conditions, soil changes, water content in the soils, to get a proper understanding of potential leaks. CO and CO2 are, let me say, products which also are resulting from photosynthesis. you can monitor with a gas sensor your success of your vegetation and let me say the health of your vegetation. Last example is even further down the line of non-visible light. It's hyperspectral imaging, so really splitting or taking the full spectrum of our light and analyzing that. And say with our eyes, we are able to monitor blue, green, and red as a very distinct wavelength and a distinct window of light. Our hyperspectral monitoring is a little bit better already, and hyperspectral is even much better. So this is currently, let me say, the outskirts of research, let me say. And you can use, again, also like the others, from a macro scale, satellites to drones, and take that even down to your surface analysis. And you are able, for example, and this is maybe something which is interesting for you, these hyperspectral imaging to distinguish different types of minerals at the surface. Not all the sensors can do that, but different sensors. And again, like I said, with the jigsaw, you need to have different tools with different capabilities to explain what you see. But you can identify, in this case, one set of silicas. Different hyperspectral sensors can do other ones, but it helps you to understand your composition of your surface in that area. And here is an example of a colleague of mine on detection of minerals in acid main drainage. You see here the image to the right in classic optical view. This is how it would appear to us when we look at it with our eyes. We identified different iron minerals up front, and if you compare the analysis of these minerals with your aerial, your spatial view, you would be able, based on the distinct fingerprint of these minerals, you would be able to separate that map into areas where you can find these three different minerals. And yeah, take that even further, the kind of post-processing of mine waste. Yeah, you could push that even so far that you identify rare earth elements in your mine waste, and you could create a business case of using your mine waste for different applications. And if you push that to a full-scale analysis, you see here a map which is a combination of different tools. Again, this is really the challenge of post-mining and also geospatial monitoring. So that map here is a result of an aerial photo of that area to create a surface model. Then he did hyperspectral flights and did some hyperspectral imaging, combined that hyperspectral imaging with lab analysis, and at the end you can create here a map of that acid mine drainage. In this case, it's colored by pH, but it could be also colored by the mineral component, and you understand spatially, and if you repeat it over time, you create a spatial temporal understanding of your mine waste. So we're coming into the chapter 2. Geo and environmental monitoring, geospatial monitoring is in principle sustainability, because we are creating a 4D image of our environment, and it helps us in sustainable land management. Surely it requires transdisciplinary, so the involvement of different experts, different disciplines to make the story right. And yeah, it helps in principle to kind of valorize former mine sites. And because you can create a lot of transparency, it's in principle also an enabler for collaboration and public participation, as I showed earlier. And with geospatial monitoring, yeah, you can create a further valorization and even new opportunities for your former mine sites. So questions to that point? I see nothing. Then I try to do now with you a little bit of an interactive exercise. Or let me say how to become a geospatial monitoring expert. And have in mind, if you see this as to be too quick this morning, you will get later these slides and you can do the exercise yourself and check out also the links in the exercise. The beginning of environmental monitoring and remote sensing environmental monitoring is in principle that picture taking December 28th, 1968. This is the rise of the Earth, the blue planet. And this was at that time the trigger for the people to kind of consider geospatial monitoring, environmental monitoring as the key to keep our planet in that shape. So what I'm trying to do with you now is in principle the integration of layers, yeah, the different pieces of a jigsaw you need to put together to get to the full story. So I want to get you now to the point to understand the process of land degradation, what we need to do here, how we can use public and open data to do the monitoring, and maybe how that works with public participation. And have now in mind, I'm using two sites within Africa. I used this exercise beginning of the year during a United Nations workshop on post-mining. And I'm doing now the analysis from here in Germany, 15,000 kilometers away from the spots you are more or less just around the corner. And I want to do the exercise with two sites now, some remine tailing storage facilities. And if you have enough time, you can do also the Mpumalanga coal fields and the fires. What I used for the analysis is open geodata. And have in mind that open geodata is available since 1972. That is older than me. And the data from this Landsat 1 missions is digitally available. I find it always extremely stunning that the data is available and we can use it nowadays. So I put you down a couple of links here, how you can run the analysis. On the left side here, the American approaches. On the right here, the European approaches. There are more systems, more sensors around. Different countries have different sensors in the orbit. Check these out. I'm sure about the South African satellites in that respect, but these ones are very famous for geospatial monitoring. And I put here also Google down because Google is very familiar to us, and you can do already a lot with Google to do your geospatial monitoring. And I found it quite interesting what I can derive with Google Earth from the sites in South Africa. So I choose these two, and just for the sake of showing it, here's the Copernicus browser. This is the data hub for the different Sentinel sensors based on the European Copernicus program. European Space Program. You can do that also with the Earth Explorer, the American one. You can zoom in. These are these tailing storage facilities, Charltonville, and you can do your work with that, pull in your details, your timeline, and you drill down through the data. You can also use the famous Worldview website of NASA. A lot of satellite imagery, different sensors is behind here, and it's based in principle just on your imagination, what kind of sensor you want to use. So let's start with site one, so the tailings. And I brought in some optical images, and I had to get, or at least try, get a little bit of an interaction with you. Please raise your hand or drop a message. What do you think you see on these images, and why I brought in these images?
Sounds like everybody is ready for a holiday. No volunteers.
No volunteers. Okay, then keep on. You would say now with this kind of Landsat image here in the top, well, that's of poor quality and you can't see a lot of things. I would say you can see a lot of things because it gives you already from 1984 a first visualization of that tailing site, and the tailings TSF was already existing. And in a very already similar shape to how it looks nowadays. So it's quite an important information that you know it was already existing 84. It's not something from the kind of, it's not just a modern development. The Google Earth I brought in because that is very, very simple. Everybody can pull up in the browser. You don't need to be a specialist on remote sensing, and you have, depending on the time at least, you have high resolution optical data. For me, 15,000 kilometers away, I found it quite interesting to see, let me say, maybe some very operational phase here till 2004, and then in the last 10-15 years, maybe a little bit of a stop on that side. Let me say beginning of an early rehabilitation maybe, but then in the 2020s some remining started. Yeah, and if you zoom in this optical satellite image, I was very stunned that I can see how the operation works and how the remining works. Yeah, and if I can do that 15,000 kilometers away, you can do that, and everybody can do that, and you can really dive into the detail of these sites. So in Google, going back, maybe not on a weekly basis or monthly basis, but in some cases we have new images on a yearly basis. So you can really see how that system is developing, and maybe also how, based on an optical impression, how the surrounding areas is developing. What I found about even more interesting is that at that site, I can use Google to get a street view impression of that site. Yeah, standing here, looking to that area, and I can tell you it looks very similar to this, because when we were beginning of the year on that site, we were kind of driving down here to that TSF and had our own, let me say, visual impression. So we didn't use special tools so far. What we have already a good impression how that site is looking like and how it's developing. with tools everybody can use, everybody's familiar with. So next time you are looking for the next pizza shop, take your analysis and check out the neighboring mine site. So public data available for everybody on the globe to check out mine sites. So if I go now further a little bit, not going into that detail here, but I use now a dedicated set of scenes beginning of this year, Sentinel-2. Sentinel-2 is the optical multispectral satellite from the EU. It has a ground resolution of about 10 meters per pixel, so a pixel can visualize 10 by 10 meters. That is on purpose because it's freely available. If you take that into the commercial arena, I was last week on a conference here in Germany on geodata and geoinformation. The satellite operator Planet was presenting there, and a company based in Germany as well in the US. They are bringing satellites up beginning of next year, and they have a ground resolution sample size of 2 to 3 centimeters in the optical and 4 to 5 in the multispectral arena. Which means that if you buy these images, satellite images, you have more or less the same resolution than an aerial photo you can buy. But the difference to the satellite is that it will, let me say, cover the site more or less once per week, which you can't do with aerial photos. But anyway, these data is freely available, can be downloaded by everybody via the Copernicus browser, the website I've showed you in the beginning. And if you compare now two special sets of windows, spectral windows, you can see that the composition of that site is changing quite a lot. And you see that different minerals are around, different chemical compositions are here around and have a very different spatial distribution. I didn't check what that means, so that would be a task you could do when you are responsible for the site. But you see that even though the picture is quite homogeneous, there are some chemical changes here at the surface. So that is important for your analysis, whether you, for example, want to understand your environmental footprint and changes to the nature. If you push that even further, you can do something on water. The NDWI, the Normalized Difference Water Index, again, a product which is available on these websites directly. No fiddling around with the data is required, just a download. You can check the legend, check the explanation, and you get a proper image. And you see here open water, which you, if I go back, you might not spot so immediately in these optical images here. So looking into these pictures here and these multispectral images here, you get a different impression on maybe the distribution of water bodies. The moisture index is another thing. You see that it's reddish color. Reddish means dry. So we are here in an overlap with these identified water bodies, but they appear here as well as do dark blue dots. This kind of other area is not so visible in that analysis. And what I find interesting, if I go back here to the detailed analysis where they used here water to blast the sediment out. So you would expect that these areas are quite wet, but you don't spot this on this moisture map. Yeah, it's still very dry. You have to keep in mind that this picture is a picture from February 24th this year with the image here. We don't know exactly when that picture is taken, and it needs to be thought about whether the position of that blast location is still available nowadays. But it helps you to understand, for example, how that tailing is behaving. In principle, I would say it's quite dry, so there's no risk that, let me say, there are fresh material on it, and the fresh material, the water is draining into the soils underneath or the subsurface underneath. Another thing I did here was I looked into aerosol mapping. Yeah, the picture I showed you in the introduction of the exercise showed that the wind is taking away the material. And if you now look carefully on that image, be aware, different scale here, you could argue with that wind direction that there is a little bit of aerosols in the south of the site. So there is some influence in the, let me say, aerosol transport in the surrounding areas. So what I did then is to take the data into a time series. I just want to give you now a little bit of an impression how that looks, and I'm going backwards now from the very recent one in February this year. I'm going now to November last year. Again, you see that it's the same site, but what I found very stunning here in November, not only the tailing site is dry, but also the surrounding areas are dry. Again, a question maybe of aerosols, the dust transported away. Unfortunately, or luckily, you don't see that in the aerosol mapping, but it might be a case also that the resolution is too high that you don't spot every single dust, every single wind blowing across these sites. Jumping back even further, in this case now a big step to 2016. This is more or less the availability of Sentinel-2. It started in 2015, and by 2016 it was in full operational mode. The site looked different at the time. Also different humidity, moisture index here. So really a time series where you can see the changes over time. So what I wanted to show you, and now I'm stopping here with site 2, is that with open geodata, and I'm going back to my slide here 60. With open geodata, you can do a lot of analysis, very simplistic for the sites on the entire globe. So being away from, being kilometers away, but you are still able to monitor mine sites in operation, but also in post-mining. You can use these data sets, these global data sets, global remote sensing data sets to create a time series and understand the processes ongoing on your mine site, on your post-mining site. And if you pull in then local data from drones, as I've shown you in the beginning, you can create even more detail, a better understanding. And if you pull in even further data, maybe operational data, you create a full understanding of the changes in your area. Be aware that geospatial monitoring requires a lot of data handling, and it requires also n-dimensional thinking. You need to understand what happened in the past, you need to understand what happens now, and you need to understand what will happen in the future to get this proper understanding. And I hope I gave you a nice overview on this. If you have questions, my contact details are on the slides. Drop me later an email. And if you want to do a deep dive, come to us and do a master program on post mining. Thank you very much for your understanding, and I'm happy to take questions.
Thank you very much, Tobias. That was so insightful, wasn't it? I didn't realize you can get that far with open data. I'm hoping we have some questions. Anyone, you're welcome to raise your hand if you want to ask a question. Okay, I don't see any now, so I'm going to ask a question. Where you're working with a large surface area as you are in Germany, and you can get quite far with the open data, how do you handle it when you need large data sets that are required across different mining houses? So you need site-specific data, but for more than one operation. How does it work in Germany to fund the creation of that data?
Yeah, that's a tricky question, Helen. So operational data from different mine sites are not available for everybody. Yeah, the mine surveyors do their, let's say, monitoring, and they submit their information to the mining authorities. If you have a dedicated request for the data, you can get access to it, but that's not normal. On the other side, a lot of historic information is publicly available in Germany. And if you are, as I said, good in playing jigsaws, already with that data, you can push the analysis quite far forward. Yeah. So I'm talking about historic maps, historical aerial photos, and then at one stage you drag in satellite imagery. So you can create quite a comprehensive view on sites where different operators are working. And if you then raise a request to the mining authorities, they can grant you access and you can pull in their data as well. Yeah, or you ask surely the mine operator itself and they provide you the data. But luckily, let me say, open geodata policy is extremely cool in Germany, so you can do a lot of stuff with open geodata.
Okay, thank you for that. We've got a few questions here in the chat box and then one hand.
Yes, let me see.
To what extent are the post-mining costs included in the operational life of the mine, or who pays for the post-mining rehabilitation?
Yeah, so we have a very strict German mining law, and the strict mining law requires that the mine operator, once he ceased operation, is responsible also for the rehabilitation, and that he has to create a very, let me say, natural state of his sites again. If you do open cast mine, yes, you can't recreate the former surface. That's impossible because you created a hole. Yeah, but even there, the mine operators are obliged to do something, run a proper rehabilitation process, and in this case, for example, create a lake, and let me say, create near natural situation again. So the mine operator has to put money aside to be able to do these rehabilitation processes. And based on the German mining law, he's responsible, carefully phrased now, till eternity for the footprint he created. So he has to put enough money aside that he's not only able to do the, let me say, rehabilitation process itself, but also the monitoring afterwards. This is how it worked with the RAG, the mine operator, and the RAG Foundation as now being responsible for the rehabilitation.
Okay, thank you. Then there's a question from Arend. He's asking if you know of any online courses that are available where we can learn how to analyze data like this.
Thank you for the interest. We are not yet there. As I said, we are changing our master program, and we are trying to put some of the modules in the master program then also as MOOCs, open online courses to the public. And we are, once in a while, we are promoting different topics on these challenges and having them dedicated workshops. But bear with me, coming up next year.
And that looks like something to look forward to. Yuri, Iman, you had a question about the water, and I think that actually warrants a discussion. If you're happy to switch on your microphone, you're welcome to raise that question.
Yeah, thank you so much, Ilian. So, Prof, thank you very much. This was really insightful. I just quickly wanted to ask you in terms of the water qualities, do you need to treat the water before releasing it into your river systems? And then just a second question as well, if you don't mind, just in terms of the imagery, maybe I missed it. In the sites you have listed, do they also then provide multispectral imagery as a layer that you can also use then for further analysis?
Question first. The mine operators need to treat their waters. To get, let me say, anthropogenic contaminations out. If we talk about geogenic contaminations, for example, salts, that is a different story. It depends then on the river where the mine water is flowing into. If it's, for example, the Rhine, and that's the reason why the pumping stations for the mine waters are in the very far west, close to the Rhine. The Rhine is carrying so much water so that you can pump your slightly salted water into the Rhine. That is not changing or affecting the quality of the Rhine water just by the amount. But in general speaking, the mine water needs to be treated. So the second question was around multispectral imagery. I don't get your question properly. So we have two sources of multispectral imagery here, at least in Germany. One source is the regular yearly aerial coverage by plane with optical and multispectral images, so high resolution data. That's done by state on a yearly basis. And secondly, we have the multispectral imagery based on the satellites. And I've shown you Sentinel-2. The same exercise can be done with the different Landsat satellites as well. And there are other, let me say, publicly available sensors around as well. So different sources, it really depends on the area where you look at, the time resolution, as well as the spatial resolution. I hope that answers the question.
Perfect. Thank you so much, Prof.
Do we have any other questions?
Yeah, maybe to give an extended answer to the last question here around the data availability. because I think that's not usual what we have here in Germany, but also in Europe. For Europe, we have very distinct regulations on geodata availability. So if the taxpayer is involved, let me say, so with the state is doing something with the taxes, then the data is available more or less for everybody. Yeah. So for example, the aerial photos is paid with taxes, so it's available to everybody. That is very beneficial because you never know what kind of smart person is sitting in front of the computer and is doing the analysis. So there might be even more value generated with these open and available geodata sets than you think in the beginning. I see that from a research perspective even better. I think open geodata is very beneficial to our work. On the other side, because the data is available and it's provided via, let me say, easy usage web services in the internet, more or less everybody can do that. Yeah, maybe not the deep analysis, but first analysis everybody can do. So you create a lot of transparency with this geodata. Yeah, and this helps a lot to, let me say, monitor industry, specifically mining, and see how their footprint is evolving, or maybe whether the rehabilitation measures are working. So in that respect, open geodata is extremely helpful, but it's maybe not usual around the globe.
Thank you.
Oh,
I
yeah,
think that sounds like a good practice approach to have the data available to the taxpayers. I hope we can move in that direction eventually. There's also a question by Sibongile.
Yes.
You're welcome to speak up, Sibongile.
Yeah, so I've shown you the application of radar satellite imagery, and with radar satellite imagery, you can monitor ground movement, and that ground movement can also use to monitor surface deformation at TSF facilities. That's definitely possible. I know several projects where radar remote sensing was used for that. It depends a little bit on the size of the TSF, but in general, it's working. You need to be in the position that you incorporate then also ground measuring results into your radar remote sensing data to be really precise on early movements that you can develop here in risk management. But in general, that's possible. Yes, and hyperspectral is able of differentiating uncontaminated and contaminated sites. With water, it's a bit difficult because water is acting like a mirror, and let me say the signal is kind of bouncing back, and therefore you're a little bit blind. But we are trying to work also here on solutions to understand with hyperspectral sensors the quality of the water. But this is research. Yeah, what can be done already is differentiation between contaminated and uncontaminated sites. Just by the composition of the chemical elements of the minerals at the surface. It works better in bare soils. In, let me say, green lands with some vegetation on it, it's a little bit difficult because the vegetation is disturbing the signal, but it's also possible there.
There's also a question about climate adaptation, a new one.
I see. Oh, I'm not a biologist, I have to say. This is a little bit out of my reach, I would say, that question. What I could answer there is where geospatial monitoring definitely helps is to get a status quo analysis of the site you want to rehabilitate, and that you understand maybe the soil composition. And then you can monitor your plants when they grow, yeah, and you immediately spot whether they are properly growing or not, so the vegetation health can be easily monitored. The satellites can also be used to identify different plant types. So if you don't know what's growing there, plants have different reflection schemes, so you can use them to identify at least groups of plants, depending again on the sensor, on the spatial resolution, but you can use remote sensing technologies to distinguish plant types and plant health. If you then combine them with a ground sensor, let me say a climate station in that area, then you are able to monitor sunshine, wind direction, precipitation, and if you have small sensors on the ground, you can even detect soil humidity, and you can compare that into your remote sensing analysis. As a special case, radar remote sensing enables you also to do soil humidity measurements, carefully speaking. So with that kind of set of tools, you are at least able to see whether you are in the position to grow certain species of plants there. Yeah. I hope that answers a little bit the question, but I'm not a biologist, I have to say. Yeah, that's a good one. The last one here. I've shown you the worldview data in my presentation. There is a remote sensing data availability on aerosols in the air. Even gas compositions is available. So for the district municipalities, it would be only the task to have somebody to analyze the data. Yeah, the data is there. There's no need for them to get out, set up their own stations on air quality. They can use the data which is available, and it's available for decades already. So they can even show the changes. Yeah. So it's only a matter of having a person who can analyze the data. But with the usage of worldview, the website worldview I've shown you, with a little bit of training, you could do that yourselves. Yeah, create a couple of maps and show that maybe the air quality is poor due to maybe dust production and so on. Does that help?
Thank you. I think that was insightful. I don't see any more or new questions. We have 6 more minutes, so we have time for one last one, or we can close the session then.
Right, thank you then, I would say. I will share the slides, or Helen will share the slides afterwards, and then you go through that yourselves. And if you have questions afterwards, drop me an email, please.
Yes, thank you very much. I think this was incredibly insightful, and I appreciated the local context that you added to the presentation, with those looking at the information and the data sets available in South Africa as well. So that was very useful. Okay, thanks everybody. Have a wonderful day further. I'm going to end the event, and like you said, Teresa will share the information later today or in this week. Thank you very much.
Thank you.
Okay, bye.